How that can be done? So first we shall start with formation of bands. How different kinds of bands are formed, that we shall see. Formation of bands. Again, I consider this simple case, lithium atom I consider. Lithium atom, you have studied the formation of lithium molecule from lithium atom according to molecular orbital approach. What you do is, you say that lithium it has 1s2 and 2s1 level. So 1s2 let me not consider. Let us say you have 2s1 level in case of lithium atom. 2 lithium atoms you consider, 1 lithium atom, 1 more lithium atom here. Let this be energy, right? So this is 1 more 2s1 electron or 2s orbital of 1 more lithium atom. We say that these two they combine to form 2 molecular orbitals. Hope you know this, right? So one it will be called as bonding molecular orbital. So this will be designated as sigma 2s. I shall just call here it as sigma. And we say that the 1 electron which is present here and the 1 more electron which is present here, that will be occupying this level. And this will be designated as sigma star. This will be empty. Hope you know this, right? So this is just when you consider 2 lithium atoms for combination. When you consider 2 lithium atoms for combination, they produce 2 molecular orbital. One will be called as a sigma or bonding. The other one it will be called as sigma star or anti-bonding, right? Now, so this can be designated. This is a very simple way of representing the same. This can be represented on a different scale, where I consider even internuclear distance between 2 lithium atoms. If I consider the internuclear distance between 2 lithium atoms, let this axis it represents internuclear distance between 2 lithium atoms. This energy levels of bonding and anti-bonding molecular level, that can be represented something like this. So this will be the energy level of bonding molecular orbital. With increase in R, it varies like this. Similarly, anti-bonding energy level, it varies something like this. Right? This is simple representation of the same thing. Now this is just by considering the internuclear distance. If 2 lithium atoms they are approaching together, if they are coming closer, how the energy of bonding and anti-bonding varies, that has been shown here. This is just for 2 atoms. Now if I want to go for metallic bond that is present in lithium atoms, it is not just 2 atoms, it will be more number of atoms. With increase in the number of atoms, so this just represents model for 2 lithium atoms. This is for 2 lithium atoms. This basic model, it can be explained for more number of atoms. Let us say I consider some 8 lithium atoms. If I consider some 8 lithium atoms, what happens, that we shall see. Say when I consider some 8 lithium atoms, the similar energy level diagram, it can be represented like this. Let this axis represent R, internuclear distance, right? So there will be four energy levels like this, representing bonding molecular orbitals. You know the basic concepts of molecular orbital theory. If you are considering 2 lithium atoms for combination, 2 molecular orbitals will be generated, and out of which 4 will be bonding, 4 will be anti-bonding. Similarly, when I am considering 8 lithium atoms for combination, totally how many molecular orbitals should be generated? 8. Always, how many atomic orbitals you combine for combination, resultant it will be the same number of molecular orbitals. Out of which 8 I have considered, out of which 4 will be bonding, remaining 4 they will be anti-bonding, and they can be represented just like this. Right? So this is a result of combination of 8 lithium atoms. Now I can just go on continuing this. When I have considered 8 lithium atoms, you can easily observe that the energy levels, they are coming close and they have started merging, right? So they have started merging. So when I go with very large number of lithium atoms, say n number of lithium atoms, what I can expect is all these energy levels, they merge together, and that merged energy level together, it can be called as band, right? So individual, if you consider, that can be called as discrete energy level. But when all those energy levels of comparable energy, when they combine together, that will form something called as band. So band, it is nothing but it is combination of different discrete energy levels of comparable energy. So if I consider n number of atoms, n means it is very large number. So for n number, I can say it like this: for n number of lithium atoms, right? So what I can expect is, this will be bonding energy level, and similarly this will be anti-bonding energy level, and these two energy levels, it can be represented like this. Here all anti-bonding energy levels they have merged, here all bonding energy levels they have merged. So these bonding energy levels, I give it different shading for that, and for anti-bonding energy level, different shading has been given, right? So if you are considering n number of lithium atoms, n by 2, they will be involved in this bonding molecular orbital formation, and n by 2, remaining n by 2, they will be involved in anti-bonding molecular orbital formation. Further, we know from lithium atom, first when we had considered just 2 atoms, bonding molecular orbital level, that will be filled, and anti-bonding level, that will be empty. So here I can say that this energy level, it will be filled energy level, this energy level, it will be empty energy level, and this can be called as LUMO, lowest unoccupied molecular orbital. This can be called as HOMO, highest occupied molecular orbital. You must have come across these terms, right? So the molecular orbital which has electrons, and above which you don't have any electrons, so that will be highest occupied molecular level, that will be called as HOMO, and immediately next energy level to HOMO, that will be called as LUMO, because it will be lowest unoccupied molecular orbital. Fine. Now, so this HOMO, whichever is formed by n by 2 sigma orbitals, this itself can be referred to as valence band. In band theory, all these sigma energy levels, here in this particular case I can say that it is sigma energy level, but in general I can say HOMO, highest occupied molecular orbitals of all atoms. In a metallic crystal, you will be having very large number of atoms. All their HOMO, they will combine together to form a structure, and that will be referred to as band, and that will be called as valence band. And similarly this one, unoccupied level, LUMO, so this will be forming conduction band, or this will be called as conduction band. This will be called as conduction band, right? Valence band, generally it will be field energy level, and conduction band, it will be empty energy level. Empty energy level. So based on these two band formation, further this band theory tries to explain all the properties of metals, mainly in connection with their electrical conductivity. What will be the situation in the case of conductors, what will be the situation in the case of insulators, all these factors they will be explained with the help of this band formation. So band, it is nothing but simply, so if I say band, it is just aggregate of closely spaced energy levels. Closely spaced energy levels. And the corresponding band, whichever is formed by highest occupied molecular levels, that is referred to as valence band. The band which is formed by lowest unoccupied energy levels, that can be referred to as conduction band. So this is how bands are formed, right? For this part, you can just refer to Hui directly. So this all these diagrams, 2 atoms first you consider, then you go for 8 atoms, then you consider n number of atoms. This is given in Hui. You can refer to this to know how these bands are formed. So this is about formation of bands and what is meant by bands. Now we shall go to the next part. How this band theory it can explain the properties, electrical properties. So based on electrical properties, we can classify the solid substances as conductors, insulators and semiconductors. First we shall try to understand what is meant by conductor, what is meant by insulator, and what is meant by semiconductor. Further then we shall proceed to the band theory to explain these properties of solid substances. Right? First, we shall see what are conductors. We know this, metals, they are good conductors of electricity. In general, we can say those substances which conduct electricity, which allow electricity to pass through them, they can be referred to as conductors. But here, if we go for, say this is just a qualitative definition, quantitative definition if I want to give, so I can say that those substances whose conductivity is in the range of 10 raised to 4 to 10 raised to 7 ohm inverse per meter. So ohm inverse, it is inverse of the unit of resistance, it is ohm. Ohm inverse, it is the measure to it is the unit to measure conductivity. Conductivity, it is taken as a reciprocal of resistivity. Maybe some other time we can see more about this ohm inverse. But at present, we just understand that it is measure of conductivity, right? Whereas insulators, if you consider, so insulators, qualitatively we say that insulators are those which do not allow electricity to pass through them. But quantitatively, if I want to say, so it should be 10, its conductivity, it should be as low as 10 raised to minus 20 to 10 raised to minus 10 ohm inverse per meter. If its conductivity value is extremely low, such substances, they can be called as insulators. Then what should be semiconductors? Which kind of substances can be called as semiconductors? What should be the conductivity of semiconductors? Should it be more than insulators? Should it be less than insulators? Or what do you expect? So the conductivity value of semiconductors, it should fall between to that of insulators as well as electrical conductors, and this value it can be given as say 10 raised to minus 6 to 10 raised to 4 ohms, ohm inverse, meter inverse. Those which gives this values for conductivity, they can be referred to as semiconductors. Now, this is just to say what are conductors, what are semiconductors, and what are insulators. Now we shall go to the band theory or explanation from band theory for each of these categories. So, according to band theory, let this be energy axis. According to band theory, we know that two different kinds of bands, they are possible in the case of substances. So, according to band theory, conductors are those substances where there will not be any energy gap between valence band and conduction band. Generally, this valence band, it will be field energy level. Conduction band, it will be empty energy level. Valence band and conduction band, they have overlap, or there is no gap between valence band and conduction band. Such substances, they can be referred to as conductors. And according to this concept, according to band theory, conduction, it is possible when electrons are free to move from valence band to conduction band. If electrons are free to move from valence band to conduction band, in such case you can expect electrical conductivity. And in the conductors, it is observed that valence band and conduction band almost they have merged with each other. Or in other words, there is no gap, energy gap between conduction band and valence band. Therefore, easily electrons they can move from valence band to conduction band, and they are good conductors of electricity. Right? Whereas, if I consider insulators, let this be conduction band for insulator, and let this be valence band for insulator. Again, here in this case also valence band it is filled, conduction band it is empty. But the problem is that here there is a large energy gap between valence band and conduction band. So at room temperature, it is not possible for these electrons which are present in valence band to jump into conduction band to give electrical conductivity. How exactly when electron jumps from valence band to conduction band, electrical conduction will happen, that we shall see. But before that, here in this case, because there is large energy gap between valence band and conduction band, electrons at normal temperature conditions, they cannot jump from this valence band to conduction band, and you cannot expect electrical conductivity. And this is large band gap, and this energy gap, that itself is called as band gap. So there is large band gap, and this band gap in the case of insulators, it will be of 5 to 8 electron volt large. So this is the situation in insulators. Right? Now, what do you expect about the band gap in the case of semiconductors? In case of conductors, no band gap. In case of insulators, it is very large band gap. What do you expect about semiconductors? So you can expect band gap, but that band gap, it will be small, right? So in the case of semiconductors, what I can say is that, so this will be empty conduction band, and this will be filled valence band, right? And there is energy gap, definitely there is band gap, and this energy gap or band gap is small band gap, and this can be said as, this will be just 0.5 to say up to 3 electron volts. If energy gap is in that range, in that case, it is possible at normal room temperature that not all electrons, in this case, since these two bands have merged, easily all electrons, they are capable of moving from valence band to conduction band. But in this case, what we can expect is, since there is some small energy gap, high energy electrons or electrons which have got more kinetic energy, they can absorb, they can be moved from valence band to conduction band, and they will be responsible for conduction. So semiconduction, it is observed. Conductivity, it will not be as high as conductors, and it will not be as low as insulators, it will be in between. So this is the explanation provided by band theory to the conduction of conductors, insulators, and this one, it is semiconductors, right? Maybe at later stages, some more aspects of this semiconductors we should see. But at present, let me stop here, and now I shall go to the mechanism of conduction. To understand semiconductivity, intrinsic and extrinsic semiconductors, we need this. So just we shall see mechanism of conduction. Before that, I'll give you values of band gap for some materials. Say it is a diamond. Based on this, you should tell me whether it is conductor, insulator, or semiconductor. You should be able to tell me band gap for this. So band gap in terms of electron volts. Capital V, it is small e. For this, it is 6.0. What do you expect? Diamond to be good conductor of electricity, or it is a very good insulator, covalent solid diamond. Its band gap, it is very high, 6.0 electron volts, so it is insulator, right? Then silicon, it has a band gap of 1.1 electron volts. Germanium, it has a band gap of 0.7 electron volts. Tin, if I consider, so all these are elements of group 14, carbon, silicon, germanium, all this. So for next, gray tin. In tin you can have two different forms. So above 13 degrees Celsius, it changes its form and it will be called as gray tin, above 13 degrees Celsius. And for this, the band gap, it comes to 0.1 electron volt. Whereas the next one, it is white tin, and this phase, it exists below 13 degrees Celsius. If you take a white tin and increase the temperature above 13 degrees Celsius, it changes its phase from white tin to gray tin, and properties of electrical conductivity property of these two, they are different. For this, it is 0. And last one, lead I can take up, and for lead also, the value of band gap, it has come to 0. Tell me, what do you think about silicon, germanium, and gray tin? Do you expect them to be insulators or conductors? right? So definitely silicon and germanium you can call them as semiconductors, but great in very less value of this one band gap. So fine, it can be called as semiconductor, or even you can call it as almost it is zero. So you can even call it as conductor, but let me call this as insulator, and these three maybe semiconductors, and these two definitely they should be called as conductors. You can observe the trend always in periodic table. Metallic character, it increases down the group. That has been observed here also. In group 14, carbon, it completely behaves as non-metal. Next you can get silicon and germanium, they start behaving as semiconductors, or they are semi-metallic. When you go completely down the group, you meet with lead, which is completely metallic in nature. Fine. Now, before I go to different kinds of semiconductors, mechanism of conduction. For this part, you can refer to a book called as Solid State Chemistry by A.R. West. I'm not sure whether you have sufficient copies of that in library or not, or even sometimes you may not get a copy in library, but all these aspects I'm taking directly from A.R. West, Solid State Chemistry, right? So now, I have said to you that you will be having valence band and conduction band. Valence band, it will be generally filled, so you can have electrons here, right? Conduction band, it will be empty. So to understand the mechanism of conduction, what we can say is that, so here nothing is present. Instead of telling that here electrons are not present, we can consider that here there are positive holes, which means electrons, they can move from this position to this positive hole position. This is just consideration. We can just say that electron, it moves from valence band to conduction band, fine, right? But to make it more clear, or to understand the physical phenomenon, always it is considered that, so in conduction band you will be having something called as positive holes, and when a electron, it moves from valence band to conduction band, simultaneously we can say that a positive hole, it moves from conduction band to valence band. Did you get the point? Right? What is really happening is that a negatively charged particle, it is moving from this level to this level, valence band to conduction band, right? So to make things easier, we can say that simultaneously, so positive hole will be present here. That positive hole, it will be moving here. Very simple. Before the movement of electron from this valence band to conduction band, here there was electron, right? When electron leaves this place, nothing is present here, nothing negatively charged particles. That can be, that hole or that position, it can be called as positive hole, right? So when this happens, what you can expect is, when electron moves from valence band to conduction band, and simultaneously you can expect from conduction band movement of positive holes to valence band. So you can expect this kind of situation, right? So electrons, they have moved to this position. Here you can expect electrons, right? Simultaneously, equal number of positive holes are created in this energy level. Further, we say that in an applied potential, these electrons, they move towards positive electrode. Electrons which have moved from valence band to conduction band, from conduction band they move to positive electrode. Similarly, we can say these positive holes, they move towards negative electrode, right? And whenever this is possible, there will be conduction. So the point that is to be noted, very important, is that if conduction should happen, in that case there should be this movement. Valence band, it should get positive holes, and negatively charged electrons, they should move to conduction band. From there, electrons, they move to positive electrode, and these positive holes, they move towards the negative electrode. right? So the one particular point that you can remember to understand semiconduction is that whenever you have excess positive holes in this level, valence band, you can expect conduction. Fine? Did you get my point? If conduction is to happen, then electrons, they should move to this energy level, positive holes, they should move from conduction band to valence band, then only you can expect electrical conduction. Now, to simplify this situation, to make things simple, I can say that whenever we have more number of positive holes in valence band, definitely it helps towards conductivity. Similarly, whenever we have more number of electrons in conduction band, they can move easily towards positive electrode, and that also contributes towards conduction, right? So this situation, it happens in applied electric potential, and you can expect conduction. So this situation, you can consider that it is before application of electrode potential. Once electrode potential is applied, the situation, electrons, they move here, and positive holes, they come back here, and you can expect electrical conduction. This can be said as a simple, or this is the simple way to explain the mechanism of electrical conduction. With this background, now we shall try to understand semiconductors. Definitely you have come across all these aspects. Maybe just how band theory explains semiconduction, that is the new thing that you are going to learn here. All other aspects I am sure that you have learned, right? So semiconductors, they are of two types. Semiconductors, they are of two types. Which are those two types? Intrinsic semiconductors. So intrinsic semiconductors and extrinsic semiconductors. Further, in extrinsic semiconductors, you have two more types. Which are those two types? This also have come across. You call them as p-type semiconductors and n-type semiconductors, right? So you know already what are intrinsic semiconductors, what are extrinsic semiconductors, what is meant by n-type semiconductor, what is meant by a p-type semiconductor, what is the example for n-type, what is the example for p-type. All these aspects, definitely I assume that you know all these aspects. And for some of the points, maybe that range, conductor range, insulator range, and semiconductor range, I have definitely referred to PU +2 book, right? Nothing wrong. Wherever you get information, so you can take information from that. Maybe tomorrow I'll be discussing crystal defects. I'll keep the main theme from that book itself, right? Some additional points I can take it from other books, other higher level books, but basic theme I take it from that itself, right? Nicely discussed and nicely classified. So you can refer to that. N-type semiconductor, p-type semiconductor, very basic aspects if you are missing, you can refer to those books, nothing wrong in that. And NCERT books, they are very, very standard books, right? Rarely you get wrong information there. So what they do is, some complicated information, they'll try to compress it, maybe some one paragraph information, they'll reduce it to 1 or 2 lines and they'll keep it there, but rarely you get wrong information, right? So at this level, you can extrapolate the things, one line you can read and what exactly they mean, you can understand that. Try to do that. Whenever you are free, try to read +1 and +2 books. I have already told you there is an app released by NCERT itself called e-Pathshala. You can download any NCERT book there, you can read that. So this comes in the first chapter of second PU named solids. In that all these aspects have been discussed, so you can just go through that. Fine. Now we shall try to understand the explanation from band theory about this for this intrinsic and extrinsic semiconductors. What do you mean by intrinsic semiconductors? First we should see something about intrinsic semiconductors. What do you mean by intrinsic semiconductor, or can you give me examples for intrinsic semiconductors? Already you have come across this. Silicon and germanium, they can be taken as, or they are the most popular examples for intrinsic semiconductors. Substance which can show semiconductivity in its pure form, right? So you are not adding something from outside here. Pure silicon and pure germanium, if you consider, by virtue of its property itself, it is semiconductor. Such semiconductors, they can be called as intrinsic semiconductors, right? So in simple words, I can say that pure semiconductors they can be called as intrinsic semiconductors. Whereas for extrinsic, to get some extrinsic, what we do is some dopants are added. If the conductivity behavior, it is due to dopants, added impurities, in that case conductivity, it will be mainly due to the substance which have added as foreign substance. So that's how it will be called as extrinsic. That conductivity property, it is induced by some external substance, extrinsic. Intrinsic, by virtue of its internal property itself, it is giving that semiconductivity behavior, intrinsic. Right? Now we shall see some aspects of intrinsic and extrinsic semiconductors. First, I'll just try to explain the intrinsic semiconductivity behavior in silicon. Intrinsic semiconductor. So by virtue, pure substance, by virtue of its property itself, it gives this semiconductivity behavior, right? So how in the case of silicon, this intrinsic semiconductivity, it can be explained. So in the case of silicon, what you can expect is, silicon, it forms, in its solid state, it forms 4 sigma bonds with 4 silicon atoms. It is tetravalent, just like carbon. Just the structure of silicon, it should resemble the structure of diamond, right? All silicon atoms, there will be sp3 hybridized silicon atoms, they will be linked to one another to form a very long network. And because of these sigma bonds, what you can expect is sigma molecular orbitals you can expect, similarly sigma star molecular orbitals, that also you can expect. Since it is making 4 sigma bonds, there will be sigma bonding molecular levels and sigma anti-bonding molecular orbital levels. All these sigma levels, they combine together and they form which bond? Which band? Which band do you expect to be formed by sigma? So this will form valence band. All the sigma star energy levels, they are combined to form conduction band, right? And definitely you can expect electrons to move from valence band to conduction band, which will be responsible for the semiconducting behavior of silicon. And the energy gap between valence band and conduction band, already it has been said to be 1.1 electron volt. It is small enough. So thermal energy, it is sufficient for high energy electrons to move from valence band to conduction band, and semiconductivity behavior, it can be observed, right? So further, one more point which I can add here is that 4 electrons per silicon atom, they are available to move from valence band to conduction band. So it will form 4 sigma bonds, because of which you can expect 4 electrons per silicon atom to lie in sigma energy level. So per silicon atom, sigma energy level, it will be filled with 4 electrons. Those 4 electrons, they can move from sigma energy level to sigma star energy level, or effectively from valence band to conduction band, right? Then one more point that I can add is, with increase in temperature, what do you expect about semiconducting behavior of silicon? Do you expect the semiconducting nature to increase or to decrease with increase in temperature? Do you expect it to increase or decrease? It will increase, because I have told you that high energy electrons, or electrons which have high thermal energy, they can move from valence band to conduction band, and they are responsible for conduction. So if you are increasing the temperature, thermal energy of the system increases. More and more number of electrons, they increase their kinetic energy. They will be able to move from valence band to conduction band. And so with increase in temperature, semiconductivity of silicon, or in general intrinsic semiconductivity, with increase in temperature, it increases. With increase in temperature, I can say that intrinsic semiconductivity, it increases, right? But there is limit. So with increase in temperature, definitely semiconductivity increases, but for a given substance there will be limit. Beyond that limit, there are so many other aspects. Crystal structure, it may collapse, right? So that limiting temperature for silicon, it is up to 150 degrees Celsius. Limiting temperature for silicon is 150 degrees Celsius, right? So maybe after 150 degrees Celsius, the crystal structure of silicon, it starts collapsing. At that time, you can expect, you may not expect increase in conductivity further. Similarly, this limiting temperature for the other intrinsic semiconductor, germanium, it is about 100 degrees Celsius. So up to 100 degrees Celsius for germanium, you can expect increase in semiconducting behavior. Right. So, very important thing, last thing, it is about the extrinsic semiconductor and the explanation for extrinsic semiconducting behavior from band theory. Extrinsic semiconductor. Fine. So extrinsic semiconductors are those materials, these are those materials whose semiconductivity, it depends, whose semiconductivity, it depends on dopants. This depends on dopants. So dopants, they are nothing but added impurities. Some impurities they will be added to increase the semiconducting behavior of the substance. So that will be called as dopant. And here, in case of extrinsic semiconductivity, dopants, they control the semiconducting property. So by increasing the amount of dopant that you add, you can even increase the semiconductivity. Whereas intrinsic, it was dependent on temperature. It depends there on temperature as well as band gap, right? So band gap and temperature, those are the controlling factors in case of intrinsic semiconductivity. But here, in case of extrinsic semiconductivity, semiconducting behavior, mainly it will be controlled by dopants, the amount of dopants that you are adding and what dopant you are adding. These two factors, they mainly decide the semiconducting behavior. Those kind of substances, they are called as extrinsic semiconductors. In this extrinsic semiconductors, you will have two different types. Which are those two different types? P type and N type. First, we shall see what is a P type. P type. P-type semiconductor, extrinsic semiconductor is that semiconductor where the added impurity, it is electron deficient impurity or electron deficient dopant. The dopant added, if it is electron deficient dopant, in that case we can expect P-type semiconductor. Why it should be called as P-type? Let us see, right? An example for this, silicon. It is a intrinsic semiconductor, and when it is doped with a electron deficient impurity gallium, doped with gallium, this gives you a P-type semiconductor, right? So silicon, it is a group 14 element. In group 14 elements, 4 valence electrons will be there, carbon family, whereas gallium, it is group 13 element, nitrogen family. Am I correct? Aluminium, previous to that, aluminium family, right, where you will be having 3 valence electrons. So if you consider this situation, say you have a gallium which is now replaced in the place of silicon. So partial structure, if I write, what I can expect is silicon, it will be having totally 4 valence electrons continuously. Before adding this gallium in this position, there was silicon, right? So it had made 4 bonds. Now when I am introducing gallium, it has only 3 electrons. It is electron deficient compared to silicon. It is electron deficient, right? So only it has 3 electrons. So what you can expect is, so one more silicon which was earlier bound to, when you had a silicon atom at the center, then that silicon atom, it was bonded to one more silicon atom. But now when you are replacing a silicon atom by gallium atom, this silicon atom, it will not get an electron from gallium to make bond. So you can say that there exists a positive pole. When you dope silicon with traces of gallium, here and there you can expect gallium to be replaced, silicon to be replaced by gallium. If silicon was present, that would have made 4 bonds. When you have introduced gallium, and gallium in its valence shell, it has only 3 electrons. So one position of electron that will be vacant, and that can be called as positive hole. This is how doping it will change the electronic structure of silicon. Now, in terms of band theory, how this explains conduction, that we shall see. Let this be conduction band and let this be valence band. Right? Already I have told you that this valence band, it will be formed by combining sigma energy levels of silicon atoms. Conduction band, it is formed by sigma star energy levels of silicon atom. Now, what you have newly created in this is that gallium silicon bands, right? So those gallium silicon bands, where they lie is, they just like their energy level, it lies slightly above the energy level of valence band of silicon. And this energy gap between valence band and conduction band in case of silicon equals 1.1 electron volt, and this new energy level created, that is just 0.1 electron volt above the valence band of silicon. Fine. This will be called as, this energy level, it will be called as acceptor level. Acceptor level. And this acceptor level, it is formed by newly created silicon and gallium bonds, sigma bonds. Now, what we can expect is, in this situation, valence band, it will be filled with electrons, conduction band, it will be empty. Whenever you add some amount of dopant, one more discrete energy level it is created, which is due to the formation of silicon and gallium bonds, and that level I had called as acceptor level. Why it is called as acceptor level? It is because this is just 0.1 electron volt above the valence band, which is filled. Now, here the electrons which have slightly more kinetic energy, they can easily move from valence band to this acceptor energy level. So this energy level, it accepts electrons, that's how it will be called as acceptor energy level. So valence band, electrons which are present in valence band with absorption of energy, they can move, or with their energy, whatever energy they have, they can move from valence band to this acceptor level. If electrons are moving from valence band to acceptor level, what should be created here? What do you expect? Because of thermal energy, some of the electrons which were present in valence band, they have moved to this acceptor level. In turn, what should it create here? It should create positive holes. Earlier I had told you one fact, that if you have more number of positive holes in valence band, that helps towards conduction. Now that is happening here, right? So here, whenever you dope it with silicon with gallium, the thing exactly which is happening, a new energy level called acceptor level, it will be created, and electrons then move from valence band to this energy level, because of which here positive holes will be created. And if you have more number of positive holes in valence band, definitely it contributes towards conduction, right? So in summary, what I can say is that thermal energy, it promotes electrons. Thermal energy, it promotes electrons to acceptor level, from VB, from valence band, and in turn this should create what? This should create what? This should create positive holes in valence band. If positive holes are created in valence band, definitely it increases conduction. This increases the conductivity. Right, this is the explanation provided by band theory for p-type semiconduction, right? And at normal temperature, as I had mentioned earlier, at normal temperature, semiconductivity, it will be created, or it will be governed, or it will be controlled by the amount of dopant that you have added, right? And the amount of dopant added, if it is more, it will help in movement of more number of electrons from valence band to this acceptor level. And the conduction, it is mainly due to positive holes in this case, right? It is not electrons which are contributing towards conduction. We have more number of positive holes in valence band which is helping us for conduction. Therefore, the conduction, it is due to positive holes, and because the conduction, it is mainly due to positive holes, it is said that it is p-type semiconductor, right? So this is the explanation provided for p-type semiconductors by band theory. Now, if we have understood this, it should not be very difficult for us to understand the n-type semiconductors. If p-type semiconductors, they are created by electron deficient impurities, which type of impurities or which type of dopants should they create n-type semiconductor? So it is electron rich impurities. Electron rich impurities or electron rich dopants, when they are added to intrinsic semiconductors, we can expect n-type semiconduction. Example for this, for n-type semiconductor, silicon, when it is doped with arsenic. Arsenic, it is group 15 element, silicon, it is group 14 element. Arsenic, it has 5 electrons in its valence shell. So what I can expect is same thing. Say, let us say here it was silicon earlier. The bonding, it was something like this. Each silicon atom, it was bonded to 4 more silicon atoms tetrahedrally with the help of sigma bonds. Now I have replaced this silicon with arsenic, right? This arsenic being group 15 element, how many valence electrons are present in that? 5, right? So 4 of them, they make bonds with silicon atoms, and this 5th electron, that will be extra, right? And mainly because of this extra electron, the conductivity increases. And how it will increase? According to band theory, that can be seen. Let this be conduction band, let this be valence band, and the energy gap in case of silicon, it is fine, 1.1 electron per volt. Now here new energy levels are created due to the formation of silicon arsenic bond, and those new energy levels, right, they have these extra electrons, and where they are located? They are located just below conduction band. And now in this case, this energy gap is as small as 0.1 electron volt. And remember, here this will be called as donor levels. Donor levels. These levels, they are created by newly formed silicon arsenic bond, and the extra electron that is lying here. So you can even show electrons here. Now what you can expect is thermal energy, easily it can promote electrons from this donor level to conduction band. In turn, what is happening? If electrons, they are moving from this donor level, which is created by donor levels, this is created from newly formed silicon arsenic bonds, right? Electrons, if they are moving from this donor level to conduction band, electrons are increased in conduction band. So if you recall, whenever valence band, it has more number of positive holes, that also contributes towards conductivity. When conduction band, it has more number of electrons, that also definitely helps towards conductivity. Now here the conductivity, increase in conductivity, it is because of movement of electrons which are present in donor level to conduction band. More number of electrons you can find in conduction band, and definitely that contributes towards conductivity. So to summarize, what I can say is, according to band theory, thermal energy, it promotes electrons from donor level to conduction band. So here thermal energy, it promotes electrons from donor level, newly created donor level, which lies just below the conduction band of silicon atoms. From that, electrons from donor level to conduction band. In turn, electrons increase in Cp, conductivity. it increases. Right? Now, the increased conduction, it is mainly due to the electrons that are present in conduction band. Earlier in p-type semiconduction, increased conductivity, it was due to positive holes which were present in valence band. That's how it was named as p-type semiconductor. Now, increased conductivity, it is due to extra electrons, negatively charged particles which are present in conduction band. That's how this can be termed as n-type semiconductor. Right? And this is the explanation provided by band theory for intrinsic semiconductors as well as extrinsic semiconductors. You can form extrinsic semiconductor by variety of dopants. It need not be always silicon. You can even take the help of germanium, and germanium doped with suitable group 13 element, it will form which type? Germanium, it is group 14 element. Group 13, electron deficient, it will form p-type semiconductor. So variety of combinations are possible. Germanium doped with suitable element from group 15, that can also form n-type semiconductor. Right? Variety of examples are possible. And as I have said earlier, all these things I have taken it directly from air-based. Right? So that is the end of the story.